These are the first notes about gas laws, and you know the drill by now. Gas laws is an area of chemistry that led to many of the things we use in chemistry, including the creation of the concept of moles, and it's something that we can fairly easily understand with simple algebra, and we'll be trying to understand one of the states of matter, the gases. Gases have their own properties. In fact, each state of matter has its own properties, but gas properties are somewhat unique because the distance between the particles is so much greater than the distance between the particles in at least solids and liquids, two of the other common states of matter. In some ways, gases behave like liquids a little bit. In other ways, they have completely unique properties. One thing that gases have in common with liquids is they are considered to be fluids. Fluids are things that flow. So obviously water flows through a pipe, it flows down a river, that's pretty obvious. But gases also flow. They flow through your air conditioner. They flow through a vent. The wind is gas flowing. So gases are fluids because they flow. In fact, one gas that you don't really want to be around, fluorine, is named that because it flows. Fluorine means it flows. By the way, fluorine is the most commonly misspelled element, so please spell it correctly. Look on your periodic table. It's fluorine, F-L-U-O. Okay, why do gas particles flow? Because they're far apart from each other. That's the main reason. So you have to start picturing things on a microscopic level if you're going to understand these gas laws. One major thing that separates gases from the other two very common states of matter, solids and liquids, is their density. Remember that density is the ratio of mass to volume. It's mass divided by volume. D equals m divided by v. And density is something you could measure for any kind of matter, because any kind of matter has mass and it has volume, so any kind of matter has density. The only exception would be a singularity, so if those exist, well, forget what I just said. But until they find those, we can count on any bit of matter having density. So gases have a much lower density than solids and liquids. This is because of the spacing between the molecules. And this, in turn, is the reason why gases behave the way they do, why they're so insubstantial, hard to get a hold of. So gas particles are far apart. Most of the volume of a gas is made of empty space. Now, this is a little different than what we were talking about before. When we talk about inside of an atom, well, of course, inside of every atom, there is mostly empty space as well. So you could really say every form of matter is mostly empty space. But what we're talking about here is the spacing between atoms. That is much, much larger than the atoms themselves or the molecules themselves. So what we're talking about here is forgetting about the inside of the atom. Just consider an atom like a billiard ball. Between those billiard balls, there is a lot of empty space. That's what we're talking about here. You cannot make the space in a liquid much smaller. That's why liquids have hydraulic pressure. So that's why you can use a hydraulic jack, like at the mechanic shop. When they lift your car up to look underneath, they lift it up usually. They'll use a hydraulic jack, which uses the pressure in an oil. Okay, squeezing it down. Well, you can't really squeeze it down. So if you push in one place, it pushes through the column of oil and up somewhere else. Well, guess what? Gases don't do that. So they call it hydraulic pressure. It's named after water, but really any liquid will have hydraulic pressure. But gases do not. So the space occupied by gas particles is actually very small compared to the volume of the gas. So it's really, really easy to squeeze them closer together. Listen, just by clapping, I just squeezed gas molecules close together. And you being able to hear this is because the transmission of sound through the air is possible because the spacing between gas molecules is very easily changed. That's what a pressure wave is. That's how you can hear this sound through the air. Okay, so applying just a little bit of pressure will very easily move the gas particles closer together and will decrease their volume. The same thing goes for expanding. They can spread out more, so gases have a variable volume. So when we think about the four states of matter, oh wait, four? Yes, there's four. Four states of matter. Don't forget what the fundamental differences between them are. Solids you're familiar with, well, think of an ice cube. Liquids you're familiar with, think of a beaker full of water or a cup of water. How about that? Gases, think of steam, water vapor coming off the top of a boiling pot of water. That's a good example. And then don't forget about that fourth state of matter. The fourth state of matter comes up quite a bit in my instruction. I hate to leave it out because there's so many things in the world you can't understand without it. You should probably already know the fourth state of matter, but in case you forgot, it is plasma. Plasma is the fourth state of matter. What is different about plasma? Well, plasma is not a gas because plasma will conduct electricity. It turns out no gas can conduct electricity because of the way gases behave. It's just not possible. So if you ever see something that looks like a gas conducting electricity, well, that must be plasma. Plasma is the most common state of matter in the universe, as far as we know. Who knows about dark matter? And it's very critical for understanding things like fusion. So I never ever leave it out of my instruction. And I'll just mention plasma briefly here because what we're here to focus on, of course, gases. So we'll just talk about the differences, okay? Solids are basically when molecules are moving very slowly. If molecules are moving slowly enough, well, then they can sort of latch onto each other, grab a hold of each other, and form a crystal lattice, or sometimes just a glass structure. But in any event, they form a solid. They will be locked down, locked in place, because molecules do like to grab a hold of each other. So if they're moving slow enough, well, they will. Think of an ice cube. So inside of an ice cube, you have a fixed volume and a fixed shape, because all the molecules are sort of locked together in a beautiful, beautiful structure, which is very much like the structure we find inside of a diamond. I'm talking about, in this case, comparing an ice cube to a diamond, not any crystal structure. Then we have liquids. Well, liquids have a little more energy than solids. They've got a little more energy. Usually that's a higher temperature, okay? So the molecules are shaking more. Well, if they're shaking too much, they can't quite grab a hold of each other. They're still trying. They're still trying to hang on to each other. So because they're still trying to grab each other, that keeps them very close together, packed very tightly, and now they can, of course, shift their position and move around, but they're still trying to get back to a solid. If possible, water would rather be a solid. If it didn't have so much energy, okay, a solid would be more stable. So of course, liquids have a fixed volume. That's because they're all trying to grab a hold of each other, not opening up spaces if they can avoid it. But they don't have a fixed shape because, of course, liquids you can pour onto the floor. You could pour them from a beaker to a flask, pour it into a graduated cylinder, pour it into any different container, and it will take the shape of the container. Gas, on the other hand, is a whole nother ballgame. Gas molecules are moving so fast that I couldn't really represent it here correctly. This is a cartoony version, of course, but they're moving so fast that they collide with each other, bouncing off each other, like billiard balls on a pool table. This opens up big spaces between them, much bigger than I'm showing here. So with the little molecules and the big spaces between them, this is what gives rise to gases' properties. So gases do not have a fixed shape. They do not have a fixed volume. They have neither, because of course they're always bouncing around. So they can take whatever volume is available. They can take whatever shape is available. They can change their shape and volume very, very easily. That's what makes something a gas. And this, of course, gives rise to the gas laws, which study the properties of a gas. Plasma is the fourth state of matter. Usually, it only occurs at very high temperatures and very high pressures, and plasma does conduct electricity. Now notice that in this example, I'm not showing water molecules anymore because technically water, when it's turned into plasma, breaks apart into its constituent elements, hydrogen and oxygen, and then they too are stripped of their electrons, and you see the electrons flying around and the ions that are formed flying around. That's what plasma's like. It's kind of like craziness. And of course, electricity can be conducted because there are actually electrons traveling through plasma. The reason I like to talk about plasma so much is so people understand how elements form. You can't really understand fusion unless you know what plasma is. It's also what we find in lightning bolts. If you've ever seen a lightning bolt, okay, thunder and lightning, what you're seeing is plasma. Because remember, gases don't conduct electricity. So how can that current travel from the cloud to the cloud, or the cloud to the ground, or the ground to the cloud? How can it travel unless it turns the gas into plasma? Now, the way that happens is a little complicated, that's true. But plasma itself is not very complicated. It's basically just ionized matter, completely ionized, so the electrons are flying separate from the nuclei. They're no longer bound to the nuclei. So plasma conducts electricity. We find it where we have lightning bolts. Well, here in Southern California, we get on average about 5 thunderstorms a year, which is about the same as the Sahara Desert. There's very few places on land that get so few thunderstorms as we get in Southern California. But most places in the world get a lot, and that's plasma. We can also generate artificial plasma in fluorescent bulbs, for example. In some of our computer screens, we can generate plasma artificially, but there's a lot of natural plasma. In fact, the sun is plasma. Stars are plasma. Picturing things on a microscopic level is one of the essential ingredients to understanding chemistry. We live on the giant macroscopic scale, like a giant Godzilla lumbering around, but really all the chemistry is happening way down deep on the microscopic level. So when I picture a gas, this is what I like to do. I like to picture a very easily conceived image of that little methane tetrahedron. Look at those little guys. Those are methane molecules. And imagine, well, what would they be doing on a microscopic level? Well, they wouldn't be standing still like that. They would be flying around really quick. They would be bouncing off of each other, colliding. That's a good way to picture what gas molecules are doing. So now notice, they bounce off each other and they bounce off the sides of this image, of this screen. Okay, well, wouldn't that push on the sides of the screen? Yes, actually it would. Each time they hit, it's a very, very light push. You'd barely notice it, but they're pushing on the sides of the screen. If they could push the screen apart, they would, but they're just not, they just don't have enough momentum to do that. So this is what creates gas pressure. And then of course, notice how they go until they hit something. Well, that explains why they can fill any volume. Take away one side, they'll just keep going until they hit the next obstacle. So this explains a lot of things about gases if you picture them doing this. If it's warmer, it's just going faster. That's the difference between cool gas and warm gas. So imagine that a warmer gas is colliding with the surface of your skin more frequently. That's one reason that it feels warmer. There's also black body radiation involved, but if it's hot, well, it's going even faster. Now it's just a blur. Imagine it's going so fast, well, this computer can't keep up with that. So that's really the difference between cool gas, warm gas, hot gas. It's just the speed that it's moving. So imagine gas pressure. Gas pressure is an interesting concept. It's a way of measuring how much a gas is pushing on any surface. You might be surprised how much gases are pushing on you, for example. So gas pressure is exactly what it sounds like. If you press, you're pushing something, and gases do that. They do it in every direction. That's the tricky part. And what generates gas pressure? Well, here on Earth, we are on the surface of the Earth. We are underneath the entire Earth's atmosphere. So the entire Earth's atmosphere is literally weighing down on us from above. And I'm using the word weigh, even though I try to avoid that most of the time, because generally we talk about mass in chemistry, but this is really weight. It's the pull of gravity on the gas above you. So imagine the gas way up on top near outer space. Okay, it's very thin, it doesn't have a lot of mass, and it would not produce a lot of weight. But that gas presses on the gas below it, which in turn adds its own, let's say, weight and presses on the gas below that, and then that adds its weight and it continues to build. So by the time you get all the way down to the surface of the Earth, we have the weight of the entire Earth's atmosphere weighing down on us. That is what generates gas pressure. It is formed by the weight of the gas above us. But because the gas molecules are bouncing off each other, bouncing off the sides like you saw in that previous image, they are not just pushing down. They actually push in all directions. They push down and they push up. They push on every side of an object because of the way they bounce randomly. So you can imagine the pressure of the Earth's atmosphere is like a giant hand trying to squeeze us, trying to squish us. So every single thing on the surface of the Earth is withstanding the pressure of the Earth's atmosphere. Okay, so we'll talk about the units of pressure in a moment, but because we are used to the standard system in the US, one way to picture this is taking a 15-pound weight and placing it on every square inch of your shoulders and every square inch of your head, every little inch on your head, putting a 15-pound weight. Well, that would add up really quickly. That would be enough to knock you down to the ground. It's actually quite a lot of pressure. But remember, the gas molecules are also bouncing back upward, so it doesn't really knock you down. It just tries to sort of squish you, okay? So every organism on the planet Earth, even a delicate little flower, is withstanding this crazy amount of atmospheric pressure. So you got to give them some credit. We are withstanding atmospheric pressure, and we're used to it. We just don't notice it. We've been doing it our whole lives. So we only notice pressure really when it changes. If it goes up, you notice feeling the being squeezed, like when you're underwater, or when it goes down, you might notice your ears popping, okay, when pressure decreases. We only notice the change in pressure because we're so used to it. So let's talk about the way we measure gas pressure. Gas pressure can be measured using a barometer, which was an invention of Torricelli, who was a student of Galileo. He figured out a very clever way of measuring how much the air is pushing on us. If you take a vacuum tube, which has no air inside it, or start off with an evacuated room with a bucket of mercury or a little bowl of mercury and put a glass tube into it, allow the air to rush back in, the air will try to squeeze that mercury. Mercury is a liquid metal. It's a very, very dense material. It's not easy to move around, but the pressure of the Earth's atmosphere will force the mercury up the glass tube 760 millimeters, which we like to call 1 atmosphere, because that's how much the Earth's atmosphere pushes on a surface. So we call it 1 atmosphere. And 760 millimeters, what is that? Well, that's 76 centimeters. Or if you want to think about it in standard system, in the crappy standard system, it's about 2.5 feet, which is quite a lot. So mercury is forced up a tube just by the air pressure, 2.5 feet. That's a lot of pressure. That's a lot of squeezing. So you might wonder, why isn't the mercury being squeezed on the sides in that image? Because the bowl is rigid. You need a rigid bowl, and the only place that the atmosphere is allowed to push on the mercury is on the surface. It's a very clever invention that Torricelli came up with. And because he came up with that, we have a unit named after him. Look, he's on the bottom of this list, the torr. Notice the unit is called the torr, and the abbreviation is torr. That stands for Torricelli. Okay, so the problem with pressure is we have so many ways of measuring it, so many different units to measure it in. We never really rectified this situation by paring them down to just one. The one that I like the most is the atmosphere. The one that is the official unit of the metric system is the Pascal. The one you're probably the most familiar with is PSI, pounds per square inch. But they're all measuring the exact same thing. The exact same thing. How much the gas is pushing on every surface. Remember, not just the top, but the sides and the bottom, everywhere, squeezing things. we have also come up with a specified set of conditions called STP, which are standard temperature and pressure, which they have set at 0 degrees Celsius and 1 atmosphere. That's the abbreviation there. ATM is the abbreviation for atmosphere. Okay? So I like to use atmospheres whenever possible. On the other hand, there are pascals, and it turns out if you look on this little chart, 1 atmosphere is equal to 101,325 pascals. That's the reason sometimes people will use kilopascals, because just regular pressure is in the hundreds of thousands. So if you change that into kilopascals, that would be 101.3 kilopascals. That's why you're going to see that quite frequently, rather than writing out all the pascals. There's also millimeters of mercury. That seems like a funny unit to use, but look at the Torricelli barometer. It's measuring how many millimeters high the column of mercury is, so that has become a unit. It actually used to be inches of mercury, which is even worse, and it turns out that under normal conditions, atmospheric pressure, 1 atmosphere, you get 760 millimeters of mercury, which is the same thing as 760 torr. If you don't like to write millimeters of mercury, you actually don't have to. You can write torr, T-O-R-R. It is an equivalent unit. And then PSI, again, pounds per square inch. Well, the reason I use that one sometimes, the reason I use PSI is because you're probably familiar with it. If you fill up a bicycle tire or a car tire, if you want to picture it in your mind, because we're used to pounds on a daily basis, that's the one I might refer to give you a sense of it. Remember, there's 14.7 pounds per square inch on every surface exerted by the Earth's atmosphere under normal conditions at 1 atmosphere of pressure. The kinetic molecular theory is a statement, a qualitative statement that describes the way gases behave. Here it is. The particles in a gas are in constant, rapid, random motion and are far apart from each other. This is a very simple statement, and yet this explains most of the way gases behave. It explains why they are fluids. It explains why they are compressible, why you can squeeze them closer together. They collide with each other, the walls of their container, that's why they produce pressure. It really explains so much about gases. So the kinetic molecular theory states that the pressure exerted by a gas is the result of its collisions with the molecules around it and the walls of the container. So imagine that gas molecules are bouncing off every surface, thousands of times per second, even more than that, of course. And every one of them doesn't contribute very much. But with all of the collisions, it adds up to the pressure we feel. So the kinetic molecular theory, again, is an underlying concept in gas laws. You need to know this statement, you need to memorize it, and you need to know what it means. Remember the word constant. That means it never stops. The word rapid is a synonym for fast. The word random means every which way, no set direction. And if you picture the gas molecules bouncing like that, always bouncing fast in every direction, and with big spaces between them, you've got it. That's the concept you need to understand gases. The kinetic molecular theory. A lot of things in science have big fancy names like this, but aren't always that hard to understand. So don't be thrown off, don't be intimidated by a big fancy name like kinetic molecular theory. It's a pretty simple concept, really. Remember earlier when I showed you the sort of cartoony version of those little methane molecules bouncing around, and that the hotter they got, the faster they were moving? Well, it's a little more complicated than that, because actually within any gas, there is a distribution. Look at these curves on here. They're almost normal distributions, where some gas molecules will be going much slower. Those would be the ones off to the left. Okay. So whenever you have gas molecules, of course, they're moving randomly, colliding in crazy ways. Some of them will be accelerated to very fast speeds because they will be hit and then hit again by another gas molecule forced in the same direction, going faster and faster, some of them could even approach the speed of sound. On the other hand, you've got some that are basically standing still because they might have been hit in one direction, moving along, and then hit in the exact opposite direction, stalled there for just a moment until their next collision. So in any gas molecule, I just want you to realize, of course, there's a distribution of the speeds they're going, which gives a distribution in the kinetic energy. Kinetic energy on the bottom of this graph is the energy of the motion. So the faster they're going, the more kinetic energy they have. Notice when we measure the temperature 25 degrees Celsius, which is the blue curve, we're basically measuring the average kinetic energy of those particular gas molecules. If the temperature rises to 35 degrees Celsius, well, that means on average they're moving faster. Some are still going very slow. Some are even more now are going really fast. But we're measuring the average temperature. So just realize that when we talk about temperature of a gas, the simple way to think about it is how fast they're moving. But just realize that there is a distribution. So it's not quite as simple as what I stated earlier. But it can be easily understood using kinetic molecular theory. Another thing that's really easy to explain now is the wind. On a very simple level, wind is the equalizing of pressure. If you have gas molecules exerting pressure in one location, and there's not as many exerting pressure in another location, okay, or the pressure is lower, well, the wind basically equalizes that pressure. The wind blows from a concentration of gas molecules, which generally produces higher pressure as long as they're moving at the same velocity, at the same temperature, and it equalizes it. So notice in this picture, I've got a bunch of gas molecules, nitrogen and oxygen, that's what makes up air, concentrated on the left side. I don't have quite as many on the right. We can imagine if they were moving, they'd all be moving at about the same speed. Well, that's got to equalize. So that's what the wind is. It's equalizing gas pressure. What causes those differences in pressure, that is more complicated, and that gets you into different amounts of solar radiation and other concepts. But for now, let's just say you can easily understand why the wind blows. Wind always blows from higher pressure toward lower pressure. So now we've laid the groundwork for understanding the gas laws. Just some basic things were introduced in these first notes about the way gases behave, the kinetic molecular theory, understanding pressure a little bit, and temperature. Now we're going to use those to understand gases in the next notes.